Welcome students to the sixth video lecture on vector analysis for B.Sc Physics first year, first semester. Today's topic is Gauss divergence theorem and solved examples on Gauss divergence theorem. So far we have learned what is del operator, what is gradient of a scalar field, what is divergence of a vector field, curl of a vector field, and in the previous class we have learned the integration of vectors. Line integration, what is line integration? What is surface integration? What is volume integration? The surface integration of any vector field gives us flux. Surface integration always gives us the normal component, the surface integral of normal component of a vector. That is nothing but flux. Amount of flux coming out of surface area in normal direction is given by surface integration. In today's class, for the derivation of Gauss divergence theorem, or the Gauss divergence theorem relates, this theorem provides a method for connecting volume integration to surface integration. This theorem provides a method for connecting volume integral to surface integral. Therefore, let us see what is Gauss divergence theorem. Gauss divergence theorem states that the surface integral of normal component of a vector, the surface integration of normal component of a vector A bar is nothing but flux taken over a closed surface. The flux is equal to the volume integral of divergence of a vector over the volume which is enclosed by the surface area. Yes. Therefore, the surface integral of the normal component of a vector A bar taken over a closed surface S is equal to the volume integral of the divergence of a vector over the volume enclosed by the surface S. This is Gauss divergence theorem. Therefore, the amount of flux coming out of a closed surface is equals to the amount of flux which is defined with double integral, that is surface integral. Therefore, surface integral of any vector field over a closed surface is equals to the volume integral of divergence of that vector field. Volume integral of divergence of that vector field is known as Gauss divergence theorem. Mathematically, it is written as double integral, that is surface integration, over a surface, closed surface, A bar dot ds bar, that is equals to triple integral over volume V, that is volume integration, divergence of A bar into dV. That is equals to triple integral over volume V of del bar dot A bar, which is nothing but divergence into dV. This is Gauss divergence theorem. Let us see the derivation of Gauss divergence theorem. For the derivation of Gauss divergence theorem, we are taking a volume V which is enclosed by a closed surface S. In that volume, we are taking a small, tiny cubical volume elements which are adjoining to each other. We are taking a volume V which is enclosed by a surface, closed surface S. In that surface, in that volume, we are taking a tiny small volume cubical elements which are adjoining to each other. There are n number of such type of small cubical elements are there in that volume V. In that cubical elements, for our consideration, we are taking a small cubical element whose sides are dx, dy, and dz as shown in this diagram. Dx, dy, dz. We have taken volume V. In that volume, n number of small cubical volume elements are adjoining to each other. In that cubical elements, we are taking a testimonial cubical element, that is as shown in figure, whose sides are dx, dy, and dz. Here I am writing the coordinate of this vertex as x comma y comma z. So the length of this side along x-axis is the dx, the length of this side along y-axis is the dy, the length of this side along z-axis is dz. Therefore, the coordinate of this point, this vertex, is x plus dx comma y comma z. Here we have taken this volume in a vector field A bar. Suppose the x component is ax. X component is ax. Therefore, the vector component at this plane 1 is considering as ax. Therefore, the value of vector at plane 1 is ax. This is x component. Now, this vector is going through this plane 1 to plane 2. Therefore, the vector field is changing. Now, we wanted to calculate the amount of flux entering into this plane 1 is the value at plane 1 multiplied with this plane area. The value at plane 1 is ax. We have taken the value at plane 1 is ax. Therefore, value is ax. The plane area is length into breadth, that is dy into dz. The area of the left face or plane 1, that is dy dz. The value at plane 1 is ax. Therefore, the amount of flux entering into the plane 1 of area dy dz, that is equals to ax into dy dz. Here, the flux is entered into the plane 1 and it is expanding to or flowing towards plane 2. Therefore, here the ax is changing with respect to x-axis. Therefore, the rate of change of ax along x-axis is dou ax by dou x. The ax component is varying, changing along x-axis. Therefore, the rate is written as dou ax by dou x. Now, here the increase in the component of ax from phase 1 to phase 2, phase 1 to phase 2, that is plane 1 to plane 2, the increase is, the increment is dou ax by dou x into dx. Rate of change is dou ax by dou x within the element dx length. Therefore, the increase or increment is dou ax by dou x into dx. Already at a plane 1, the value is ax. Therefore, increment is dou ax by dou x into dx. Now, we can write the value at plane 2 is already value, existed value is ax. The increment is dou ax by dou x into dx. Therefore, the value at plane 2 is ax plus dou ax by dou x into dx. Now, we are calculating amount of flux coming out of plane 2. Here at plane 2, the value is ax plus dou ax by dou x into dx. It should be multiplied with area, we get flux. Therefore, the flux coming out of the right face or plane 2 of the area dy dz is given by ax plus dou ax by dou x into dx multiplied with surface area, that is dy dz. Now, the net flux along x-axis is the coming out flux minus entering flux. Coming out flux is ax plus dou ax by dou x into dx into dy dz minus ax into dy dz. Here, performing just a simple subtraction, ax dy dz minus ax dy dz cancelled. Therefore, remaining quantity is dou ax by dou x into dx dy dz. Therefore, the net flux along x-axis is given by dou ax by dou x into dx dy dz. Similarly, the flux along y-axis can be written as dou ay by dou y. The component along y-axis is the ay. Therefore, dou ay by dou y multiplied with small volume element, that is dx dy dz. Similarly, we can write the flux along z-axis is dou az by dou z into dx dy dz. These are all the flux components along their respective axes. This is along x-axis, this is along y-axis, this is along z-axis. In small cubical element whose sides are dx dy dz and whose volume is dx dy dz. Therefore, the total flux coming out of that volume element is given by the flux along x-axis, that is dou ax by dou x into dx dy dz plus flux along y-axis, that is dou ay by dou y dx dy dz plus flux along z-axis, that is dou az by dou z into dx dy dz. In all these three terms, dx dy dz is common, therefore take it out. Therefore, the total flux coming out of the volume element is d phi, that is equals to dou ax by dou x plus dou ay by dou y plus dou az by dou z into dx dy dz. This is the flux coming out of small volume element. But I wanted to calculate total flux which is coming out of entire volume. To calculate the flux which is coming out of entire volume, what I have to do? I have to take the volume integration over d phi. I have to take volume integration over d phi. Therefore, volume integration of d phi, that gives us the total amount of flux, that phi, that is equals to volume integration or triple integration of dou ax by dou x plus dou ay by dou y plus dou az by dou z into dx dy dz. Say equation 1. This is the total amount of flux which is coming out of the entire volume V enclosed by a closed surface S. Now let us see the flux coming out of area. This is already discussed in surface integral in the previous class. That is, the surface integration of any vector field over the surface area gives us the flux coming out of the surface in normal direction. That is, the flux coming out of area S occupying by volume V is given by the surface integration of that vector field. That is, double integral over surface S a bar dot ds bar. Say this is equation 2. This is the flux. The equation 2 gives us the flux coming out of area S enclosed by or occupied by a volume V. In previous equation, that is in equation 1, the total flux which is coming out of entire volume which is enclosed by the surface S. These two are equal. Naturally, these two are equal because the flux coming out of area S occupying by a volume V must be equal to the flux coming out of volume V, because the flux in this element is, any element here is conserved. Therefore, equation 1 is equals to equation 2. So, equating equation 1, equation 2, we got double integral over surface S a bar dot ds bar, that is equals to volume integral dou ax by dou x plus dou ay by dou y plus dou az by dou z into dx dy dz. This dx dy dz is the volume element, volume of the small cubical element. And you know well, dou ax by dou x plus dou ay by dou y plus dou az by dou z is nothing but divergence of that vector field. That is written mathematically del bar dot a bar. Therefore, this equation becomes double integral or surface integral a bar dot ds bar over surface S is equals to volume integral over volume V del bar dot a bar into dv. This del bar dot a bar is nothing but divergence. Del bar dot a bar is nothing but divergence. Therefore, this is the mathematical expression which we have seen at the statement of Gauss divergence theorem. Therefore, Gauss divergence theorem is proved. This is Gauss theorem of divergence or Gauss divergence theorem. So here, Gauss divergence theorem relating this double integral to triple integral with the help of divergence. Gauss divergence theorem here relating surface integration of a vector field to volume integration with the divergence of the vector field. So, double integral is relating or equating, surface integration is equated with the volume integral of divergence of the field. That is Gauss divergence theorem. Let us go for few numericals. Evaluate double integral r bar dot n cap into ds, where S is a closed surface. S is a closed surface. So, this numerical can be solved by Gauss divergence theorem. Gauss divergence theorem. By Gauss divergence theorem, we know that surface integral is equal to volume integral with divergence. Therefore, r bar dot n cap ds, that is equals to volume integral divergence of r bar into dv. So, divergence of r bar, divergence means del bar dot r bar. Therefore, del bar, that is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z dot r bar, that is xi plus yj plus kz, where r bar is position vector into dv. So here we have to perform dot product. By doing dot product in between these two quantities, you get I dot I, that is 1, dou x by dou x plus j dot j, that is 1, dou y by dou y plus k dot k 1, that is remained is dou z by dou z. into dv. But dou x by dou x is 1, dou y by dou y is 1, dou z by dou z is 1. 1 plus 1 plus 1, that is 3. 3 into dv. 3 into triple integral of dv. Triple integral of dv is nothing but the total volume of the surface. The surface which is enclosed, the volume element is triple integral of dv. Therefore, that is equals to 3 into v, where v is the volume enclosed by the surface. Yes. In this way, we are using Gauss divergence theorem to solve this numerical. Let us go for second example. If S is any closed surface enclosing a volume V, and that surface is represented with a vector function f that is equal to xi plus 3yj plus 2zk, show that double integral s f dot ds that is equals to 6v. 6v. So this is very similar to previous problem. Now let us calculate del bar dot f bar. That is equals to del bar, that is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z. The field is given as xi plus 3yj plus 2zk. Therefore, here we are writing the field xi plus 3yj plus 2zk. So performing dot product, then I dot I, that is 1, dou x by dou x plus j dot j, that is 1, dou of 3y by dou y plus k dot k, that is 1, dou by dou z of 2z. So here dou x by dou x, that is 1, dou by dou y of 3y, that is 3, dou by dou z of 2z, that is 2. What we get here? 1 plus 3 plus 2, that is 6. Therefore, substituting this value in Gauss divergence theorem. What is Gauss divergence theorem? Double integral f bar dot ds bar, that is equals to triple integral del bar dot f bar into dv. That is equals to, here we have calculated the divergence of the field, that is a 6 dv. Taking 6 out, the triple integral of dv, which is nothing but the volume enclosed by the surface S. Therefore, this is equals to 6v. We have performed these two numericals in a similar fashion. Let us go for third one. Here, find double integral f bar dot n cap into ds, where f bar is equals to I into 4xz minus j into y square plus k into yz, and S is the surface of a cube bounded by, here the values are given, x equals to 0, x equals to 1, y equals to 0, y equals to 1, z equals to 0, z equals to 1. Here cubical element boundaries are given. Therefore, the side of the length will be unit. Therefore, according to Gauss divergence theorem, double integral of f bar dot n cap ds, that is equals to triple integral of divergence of that vector field into d. Therefore, you know divergence of f is given by fx ifx plus jfy plus kfz. Suppose here we are taking the divergence of f, that is dou fx by dou x plus dou fy by dou y plus dou fz by dou z into the volume element, which is nothing but dx dy dz. Here the x component, that is 4xz, fx equals to 4xz. I am substituting fx value 4xz here. Fy value, that is minus y square. I am substituting minus y square here for fy value. See, fz value is yz, therefore substituting yz here and performing partial differentiation. Dou by dou x of 4xz, that gives us 4z, because x is partially differentiated. Remainder dou x by dou x is 1, remaining quantity is 4z. You go for the second term, dou by dou y of minus y square, that is minus 2y. Next, the last is dou by dou z of yz, dou z by dou z, that is 1, therefore remainder is y into dx dy dz. So the final value is 4z minus 2y plus y. Minus 2y plus y, that gives us minus y. Therefore, 4z minus y into dx dy dz. First, I am integrating with respect to z. Therefore, integral 0 to 1, 4z minus y dz. That gives us 4z square by 2. That gives 2z square. 4z square by 2 minus y into integration of dz. That gives us z. And applying the limits 0 to 1. So here writing upper limit 2 into 1 square, that is 2, minus y into 1, that is 1. 2 minus y. If you apply lower limit, that is 0, there is no need to write that. Therefore, the remaining quantity is 2 minus y into dy dz. Here again we are doing with respect to y the integration. Therefore 2 into dy integration, that is y, 2y, minus integration of y dy, that is y square by 2. Therefore the integral value of 2 minus y dy is 2y minus y square by 2. Again we are applying the limits 0 to 1, that is upper limit 2 into y, 2 into 1, 2 minus 1 by 2. 2 minus 1 by 2, that is 3 by 2. 3 by 2 into dx. Doing integration, dx value is x here. 3 by 2 into the limits is 0 to 1. Therefore, the final result is 3 by 2. Therefore, we are just performed the divergence here and integrated thrice with respect to z, y and x and substituting the values, and we got the final answer. Next, go for the fourth example. If f bar is given by IAX plus JBY plus KCZ, where ABC are constants, show that double integral f bar dot n cap ds, that is equals to 4 by 3 into pi into a plus b plus c, where s is the surface area of a unit sphere. Here this is very important. Here the volume is depends on the geometrical shape which is given in the problem. In previous case the geometrical shape is cube. Here the geometrical shape is sphere. According to Gauss theorem, the double integral of f bar dot n cap ds, that is equals to triple integral of divergence of vector field into dv, where v is the volume enclosed by s. Therefore, substituting the vector field value here, del bar dot IAX plus JBY plus KCZ. Therefore, writing del bar equals to I dou by dou x plus j dou by dou y plus k dou by dou z. Doing dot product, we got dou by dou x of AX plus dou by dou y of BY plus dou by dou z of CZ. Here, the remaining value is, after doing partial differentiation, dou by dou x of AX, that is A, dou by dou y of BY, that is B, dou by dou z of CZ, that is C. So, A plus B plus C into dV. Taking a plus b plus c is the constant, taking out the triple integral of volume dv. Here we know that the volume of a sphere is 4 by 3 pi r cube. Volume of a sphere is 4 by 3 pi r cube. But the sphere's radius is taken as 1. Therefore, the value is a plus b plus c into 4 by 3 into pi 1 cube, that is 4 by 3 pi. The remainder value is 4 by 3 into pi into a plus b plus c. Why we are taking radius 1? Here in the problem, the surface area of a sphere, which sphere? Unit sphere. That means the radius of that sphere is 1. That is why we have taken the radius is 1. So the final answer of this volume integral is 4 by 3 into pi into a plus b plus c. We have proved that. Now the time for assignment: state and prove Gauss divergence theorem. This is the very important question for the examination point of view. State and prove Gauss divergence theorem. Thank you for right now.